which side I'm on now. It should be, it's a different view. Okay, let me just dive into it. Basically, yesterday I fried this by powering my synth because there was some short, and I don't exactly know what the cause is, but basically I rebuilt it. This one's much cleaner. Look at these beautiful traces. But I repaired this one too with this jumper wire because one of the things broke, and then I replaced one of the voltage regulators, which was faulty. So I'm going to attach one of these to here so that we have, basically this one will go in the synth. It's all pretty and nice, and we'll mount it. This one, however, will be my benchtop one, where I can just use it to, because it's annoying to have to take it out of the case or like wire it through the case just to be able to test the module. So it does make sense to have two power supplies. That said, we need to figure out which is which. So first thing I'm going to do is I have a AC to 15 volts AC transformer plugged in over there. So I'm plugging this in, and I'm setting my multimeter to AC voltage, and I'm just going to see which leads give me which. And basically my plan is, okay, so that's 15. What is this one? That one's like point. That one's like nonsense. So I tried shorting them. I thought I would feel a buzz, but nothing. Okay, so I think it was not this one. So it was. So I'll make this red and this black. Oh, wait, no, I bent the wrong one. Okay. Maybe that's why I didn't get shocked. Alright, let's see. Nope, no shock. Sad. Alright, so that's good. So we're going to just clip this onto here and then make some wire. And then solder it on. Alright, so I'm going to make them kind of long, I think. Okay, so now we'll put black over here. And this looks like the type of stuff that is really annoying to solder to, but we're going to find out. Okay, so they're hanging. We can turn on our power supply or our soldering iron. Wait for that to heat up. Oh, I don't have my paper towels. Paper towels are useful. Dun, 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 dun. Actually, what I'm gonna do, I'm gonna pull this. Okay, probably hot now. Yep. I really fucked up this tip when I okay, well, it should be tinned now. This stuff is such a pain to solder too. Oh, actually, this stuff is good. This stuff is really good. Okay. Beautiful. Okay, so now all we have to do is plug this in the right spot. I forget what is what. The diodes goes to red, so we can plug it in there. And then ground is 2 down, I think. 2 doors down. Is it that? Is that ground? Fuck, I'm such a dip. I'm a donkey. Donkey. Okay, let's see. Okay, that's right. Okay. Fucked it up. Okay. Okay, it's good enough. This shit is not going into a fucking nuclear plant. Alright. So now we're gonna just say fuck it and see if it works. What's the worst that could happen? The worst that happens is we break something. Okay, so this one is flipped around, so ground is on the centermost, then plus 12 is here. Alright, so we're gonna do that. Turn it on. Set it to DC voltage. Get our plug. Nice. Minus 19. How's that possible? I don't really understand that. So that means that our peak to peak is going to be high too. 30 volts peak to peak. That's not good. How is that possible? Probably can't see it, but 18. That means we can't really use it, right? I don't think my components are rated for such high voltage. Something seems suspicious. Damn. The plus 12 was working perfectly. Wonder what's wrong. I took out one of the caps, but that shouldn't mean anything. Okay, let me ask GPT. It's just fucking victim blaming me for having bad components and shit. I don't think that's it. I think I'm a little low. How about that? Test. There we go. No, we just tested. I mean, I did hear a click. Let me. I want to desolder this cap again and see what's up. How do we do that? I guess we'll do it like this. And then I'm just gonna hold on to this. This shit sucks. Fuck. Don't move muscle. It's impossible to get it out of there, man. I feel like this thing won't be able to measure capacitance that high. Dude, the crows go crazy. Oh, we're gonna have an issue, bruh. If they perch in the far tree, we're good, but otherwise... Dude, the crows this time of year go crazy. Okay, so we need to go to capacitance mode. Okay. I don't really know. Alright, wait, I'm gonna unplug one of them and let's just measure it again. I'm just curious if having one of the capacitors dead actually did something. Wow, it measures the capacitance? That's cool. Alright, come here, baby. Should I try replacing it again? Honestly, I kind of think I should just say, screw it. Oh, here it is. I think I'm gonna just test. Test the new one. If it breaks, it breaks. Like, it's not the end of the world. Oh wait, actually I have a tool. Okay. Can y'all see this? So somehow these are hot. Oh, they're not really. Oh yeah, it's just confusing. Okay, so what I'm gonna do is I'm gonna use the infrared camera, and I want to record actually. Okay. Alright, so let's get this all sorted. Alright. So I replaced the Schmidt trigger, and I had my dad sort of look at the circuit. And he said that there shouldn't be any problems. So if we fry it again, it'll suck, but... Okay, so basically we want to see if anything heats up when we do this. So, oh fuck. So we need to make sure that this is... Okay, and we really want to do this correctly so that y'all can see it. Okay, I'm gonna hold it like this. We don't really have much time though. I wish I could do this. I guess I can do this one-handed. Fuck, it keeps fucking iPhones, bruh. Nothing's getting hot. Look at the power supply. Let's look at the voltage regulators. Nothing seems hot. Okay. Okay, well that was something. Alright, so it should be running. So I'm actually going to unplug this, and we're going to get the oscilloscope, and we're going to see maybe just changing the chip. Maybe just changing the chip fixed it. Wait, I actually totally forgot. So I got the oscilloscope, that's fine. But I forgot that there's a capacitor I took out. Alright, so let's unplug this. Get this out of the way for right now. Okay. See if this will slot in. Oh yeah, you gotta bend the legs a little bit on these guys. Okay. Okay. Alright, let's try this shit again. Hot cross buns. Hot cross buns. Okay. Let's get this thing fucking going. Okay. Oh, it must have turned off. Okay. Bro, this thing sucks. There we go. Is there anything actually hot? Or is it just because I... Oh, right. It's hot because of the solder. Alright, so I'm going to click record. It's at 27 degrees. I don't think it's that big of a deal. Okay. So all we did was change the chip. We plugged it back in. So now... It's not ideal. Okay, so it's going. I'm going to unplug it. Plug in our thing. Plug in our thing. Guys, let's hope that this works. Because if this works, then I can get on to doing something cool, like making the front panel. I'm going to make a second front panel. I think I'm going to make this one out of aluminum. 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 You know, so wait, hold on. This big wave forms. Scope. All right. Oh, wait. Was that out the whole time? Fuck. I don't know if that was out the whole time, so we need to do it again. Oh, beautiful. That worked quickly this time. Recording. Okay, nothing's hot. Somehow it disconnected. This thing kind of sucks. Okay. Whatever happened, I don't care. I'm so nervous now. I'm a little nervous Nelly. Nervous Nelly. Oh, should I do ground testing again? Let's just see. Well, that sucks. Wait. What did I just see? I feel like I saw... Something's happening. Wait, okay, wait. If this really is the case, then this should do something, but it doesn't. No, I think it's a bunch of hocus pocus. Is it just oscillating super slowly? Done. 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 Bruh. Okay, hold on. Everybody shut up. No way. Wait, it's working. It's going from minus 5 volts to 5 volts. Okay, wait, hold on. Let me change the duty cycle. I think the lack of that 100K resistor is, I think the frequency is just super low. Guys, are we on to something here? I mean, that's not right. Well, okay, let's try to apply a CV. I'll get the breadboard and we'll see. I'm gonna unplug this. Okay, so we have a breadboard with a potentiometer. So what we're gonna do is we're gonna plug into here. Probably can't see that. Okay, then we're gonna plug this. Into here and into here. Now we need some jumpers. Jumper dumpers. Dumper jumpers. Okay, here's one. Okay. Wait, actually, I'm gonna put those over here. Okay, now we need to get some batteries. Butter. Okay. Wait, is it on? I don't think it's on. Okay, that's fine. Guys, this would be so freaking hype if it actually worked. Okay, so what are we doing here? We're gonna plug it in. Oh wait. Everybody stay fucking calm. Okay, wait, I'm gonna unplug it. Dun-dun-dun-dun, dun-dun-dun-dun, dun, dun-dun-dun-dun. Okay. Alright, so now that's going. Let's power this thing. Fuck, man. What was happening? There was something happening. But now nothing is happening. I guess we'll have to go back to check for broken traces. What? Excuse me? I just tapped the via. Oh my god. Hold on. No way. Excuse me? But this isn't right. Something fishy is going on. Nothing, nothing, nothing. Perfect square wave. So I want to get my speaker. I'll show you guys it's sort of working. Alright, cool. Alright, so we're going to plug this baby into the square wave output. And then we're just going to... You can't hear anything? Can't hear anything? Then all I'm going to do is touch the antenna. Okay, wait. So now what we want to do is we want to listen to that and then plug. No, that's just pure noise. Oh wait. Okay. It's so weird when I touch this thing. But it doesn't change pitch, so it's clearly... I don't get it, man. Why does this work? Why is it that it... But the thing is, it doesn't even matter because it's like... Voltage control doesn't do anything. Okay, let me open up the schematic really quick. Which output is the pin 7? Or rather, pin 8. Okay, so I need to... This is pin 8? Okay, so let's go to the OSI. Try to hook on the... Touch this thing. I'm so confused. Okay, and then which one is the pin 14? That's that one over there. Fuck. Wait, is that square out? No, see, that's an indication that this is totally fucking messed up, man. But I feel like I was getting a sawtooth somewhere. Like if I take this and connect it to here. Wait, but I have to take out the current draw. I guess. Dude, I'm at a loss, man. What could it be? The thing that's crazy, though, is that the comparator's duty cycle was changing, right? Like, if we go to pin 7, which is this. Let me touch this. Let's make sure that... Okay, so there we have that. Let's see. Does the duty cycle actually work? It does work. Wait, if I just touch this thing? Okay, so I'm just going to ask GPT. Let's see what's up with this thing. I'm building a voltage control oscillator, and I have a PC board, and if I don't even know how to describe this, man. If I touch this via, then the square wave works, but the sawtooth wave doesn't work at all. But the square wave works, and the pulse width modulation works, but it doesn't make any sense because the way that this is designed, is that the square wave takes the triangle, the sawtooth wave, and feeds it into a comparator setup using an op amp. So hypothetically, if the pulse width modulation works, then we should see a triangle wave. But for some reason, the pitch control just does not work at all. Okay, wait, let's go to this pin. Okay, let's go to this pin. Click on there, and then touch it. Okay, but no sign of life with... There's something obvious that I'm missing about.
Yeah.
Hey, when do you get back?
Oof, that's a hard question. Maybe 6?
Okay, this is so weird. When I touch this thing, it sort of works, but it sort of... it's a very confusing thing.
Okay, we'll debug it.
All right.
Goodbye.
Bye.
Read your book. Read art.
Yeah. Oh, fuck. All right. Okay, so there's a bunch of shit to debug that I don't understand. Wait, let me get my voltmeter. I want to see that these batteries aren't dead. That would be fun. Be a fun little discovery. Nope, it works. It's a bummer the pitch control doesn't work. Could it be the transistor pinouts are fucked? No way, right? Alright, I want to fix this one joint. Wait, but what am I doing? I'm just trying random shit like a fucking dumbass. Oh boy. Okay. Oh boy. So that should be connected to the same thing. Wait, hold on. So we want to go here. See, that's confusing. Somehow this is getting grounded. Damn, I don't know what I did with that tiny screwdriver. Because I want to know if this trimmer pot was like set to 0. Bro, this is such a mess, dude. Get the power supply. I'm gonna plug it back in just because. Where's my scope? What's it on? It's on this stupid fucking thing. What happened? What did I do? I messed with it and now it's fucking broken. Oh wait, power fell. Okay. So now we do this thing and we get a square wave. Okay, so that is so weird. The weirdest part about this is that I get pulse width modulation. I mean, something's broken about it, but we're getting PWM. Yeah, I wanna put my probe on. I wonder if my transistors have the wrong. For some reason, oh, Jesus Christ. This is impossible, dude. You like really hold this in here. Okay. and get okay, now we got that guy. Now we want to turn this. I don't know. Could that be a cold solder joint? I feel like it's not because of how I really want something to work, so I'm gonna bring the box out here and we're gonna mess around. Okay, so we got the box here. Now we're gonna take. Okay, this is gonna go to CV. Okay. Hit CV. Now, how are we gonna do this? Let's move everything underneath this. We'll take these out. Let's hope this thing works. Okay. Huh. Okay. So now doesn't matter. Black. All right. Please, please, please work. Nice. Oh yeah. Oh, bro, I'm such a dumbass all the time. Okay. Nice. We're just forgetting. Well, that's satisfying, I guess. Not really. Let's see. Wait, normal. what are we doing? I think I'm gonna go to KiCad and we could probably build the envelope generator. The thing about the envelope generator is that
if you've been following this channel for a while,
we can just do EG. Alright, so maybe we'll just design an envelope generator. The thing is, the thing about
and build
this,
along with my videos, chances are you've now got a VCO, a filter, and maybe a VCA in your DIY module.
bruh,
And
no,
while
I
these
don't.
are essential modules, they're not all that usable without another important addition, an envelope generator. Why is that? What do we need an envelope generator for? Simple. We've only got two hands, best case. So there's a hard limit to how many knobs we can turn and parameters we can tweak at the same time. Also, those hands are generally sluggish, sloppy, and imprecise. Wouldn't it be much better if we had some virtual programmable robot hand to help us out that would do what we tell it to do reliably and precisely whenever we want it to? If your answer is yes, then you might be a control freak. Also, you'd probably want an envelope generator, like this one.
maybe we'll just breadboard this out.
So what exactly is happening here? Simple. This envelope generator is acting as a virtual hand, tweaking a cutoff frequency, an amplitude, a pitch. How does that work? Well, in both my oscillator and filter series, we went to great lengths to make them voltage controllable. This pays off now, because both for the oscillator's pitch and for the filter's cutoff frequency, we now have two interchangeable options if we want to manipulate them, by turning a knob or by sending a voltage into these inputs. So if we want the filter to open up, for example, we can either turn this guy to the right, or we send in a high-level voltage here. Now, of course, if we only wanted to open the filter and keep it open, we could send in a fixed 12-volt signal and be done with it. That's not all that useful, though. Normally, you'd want the filter to close at some point, too. So why not simply use a square wave oscillator? Since a square wave is really just an oscillation between a high and a low-level voltage, this would indeed cause our filter to open up and close down. Even better, it would do so rhythmically, as the oscillator cycles through its phases. And while this does work, it has two severe limitations. First, the opening and closing movements are always instant, with no way of making them any more gradual. This might be what you want in some contexts, but often you'd need something less abrupt. And second, we can't change the rhythmic pattern. All we get is a constant staccato. Here's what that would sound like. I'm using a very slow square wave to control the filter's cutoff frequency. Now, I don't know about you, but to me, that sounds very static and lifeless. So what can we do about that? Well, the most obvious thing is to try and make the rising and falling edges here less steep. In envelope terms, we'd say that we want to slow down the attack and extend the release. And while this may sound complicated, it's actually anything but. All we need are two components, a resistor and a capacitor. Setup should low pass. Swap here, the resistor and into the input. So there, the two would induce. Try this, we'll have to think about the appropriate values for the capacitor and resistor. Now, since we're dealing with a very, very slow square wave oscillation at the input, they'll need to be pretty big. Otherwise, the effect will be so minimal that we won't be able to tell the difference. In my experiments, a 100K resistor coupled with a 1 microfarad capacitor gave me some decent results. So I'll set this up on my...
So wait, what did he do? He sent the square wave to the low pass filter, and then that was sent to the cutoff.
In my experiments, the input square, let's see how it sounds. And yeah, the filter movement is much less abrupt. We've got a slower attack and an extended release as planned. But what if we want to adjust the effect? Well, we've essentially got two options here. We could change either the capacitor or resistor value. But because switching components is not the most user-friendly strategy, I'm going to replace the fixed resistor with a potentiometer. This way, in process. And yeah, we can now dial in a more or less intense effect. The only problem with this is that the attack and release phases are not adjustable independently. Changing one will always also change the other. So how can we separate the two? Our capacitor phase gets their own. So when the input signal swings high, a current will flow through this diode, and only this diode, through this resistor and into the capacitor. And during the low phase, the current will take this other path. This means that this potentiometer now controls the attack, and this one controls the release. Capacitor.
I don't really get the LFO as envelope thing, because the LFO is going to play it again, right? Like, don't you only want to play the envelope once?
As you can hear, I'm now able to sculpt the filter movement much more freely. Great. So what we have here is an ultra-simple passive attack-release envelope generator. There's a problem? That very much depends on what your goals and context are. In this current form, the envelope can only properly function if two external conditions are met. The circuit triggering it, in our case, the oscillator, needs to be able to provide enough current. And the circuit we're controlling, in our case, why? Simple. Let's imagine we put a 100K resistor between our square wave oscillator and the envelope. This way, we are severely limiting the amount of current flowing into our circuit. And that means that even if we dial our attack and release pots all the way down, charging and discharging our capacitor here will not be instant as we'd expect, but instead would take a while. On the other side, imagine our filter was also using the envelope to drive an LED. Since LEDs are pretty power hungry, this would basically suck our capacitor dry, and then eat up all the current coming through the attack pot, turning our envelope curve into a pretty flat line. Now granted, this is a worst case scenario. Well-designed modules should always have high current outputs and low to no current inputs, which ironically is a standard our envelope here does not live up to at all. It eats up our oscillator signal while providing nothing for the filter. Thankfully, fixing that is really straightforward. We'll simply buffer both the in.
Yeah, but the thing about this that's annoying to me is that he's just using potentiometers. Like, you can't control the envelope modularly, right?
And output with
Like, this isn't really a modular envelope generator. It's more of like...
op-amps. Now, if you don't know how these work, I've put a link to a thorough explanation in the description. But the basic gist is that if you set op-amps up like this, they act as what we call voltage buffers. These things take in a voltage and provide an identical copy at their output, while being...
But I guess...
Hello everyone, this is a short update of the latest module that I have finished, an envelope generator. It's based on René Smith's design, fastest envelope generator in the West, and I think that is a really cool...
What is that, 555?
design because it basically uses every feature of the 555 timer to build up an ADSR envelope generator. And I know that there are probably 100 different versions of this, or located in different GitHubs and whatnot. But I still wanted to make my own version of it. And it's basically René Smith's design without any changes. I only added a LED basically.
Dude, that is so clean.
Yeah, as you can see, there is most of the components are surface mount components. I started to build this on a breadboard, and that was just to check that the TLC 555 timer that I selected instead of using the interseal IC.
Dude, that's a nice thing. Maybe I should build one of those. Just something with
TLC 555 timer that I selected instead of using the interseal ICM 75.
What is that? That's a function generator?
Instead of using the interseal.
No, that's a modular rack.
ICM 7555 that René uses in his design. I just wanted to check that the TLC 555 works, and I had no issues at all. It worked perfectly. So after that, I proceeded with the PCB design, and I also made a PCB panel for it. I tried to do the design as compact as possible, so I can fit a lot of these in my Euro rack. And after a couple of weeks, the PCB has arrived, and I started to assemble a prototype. The build-up of the module is very simple. Everything is mounted on a single PCB, and since I'm using SYNTH components for the most part, I could fit all components on one side of the PCB and put the pots, jacks and LEDs on the other side as through-hole components. SYNTH can be a little bit tricky to assemble or solder onto a PCB, but I use the method that I take the most difficult components first, like the semiconductors, diodes, transistors, and ICs. And after that, I take care of the rest of the discrete passive components like resistors and capacitors.
Damn, bro.
I do the through-hole mounted components. However, when I finished the first prototype, I discovered that I made a stupid mistake in the schematic diagram. So I have flipped the pots in the schematics, and it turned out that the pots were sort of operating in the wrong direction, which made it really difficult to use. So I had to fix that and make a second board spin. And I also discovered that since I'm using linear pots for AD and R, those parameters or those slopes can be a little bit tricky to set sometimes. So if you are planning to build this, I think that log pots would be beneficial.
See, what I would want is that you could modulate the attack. Like, for instance, let me pull up Ableton and I'll show you guys what I mean. I guess I mean like this. Or I could do this. Anyways, that's what I mean. Okay, wait, but let's go back to this thing. So I guess because I'm wondering how you can replace the pots.
Being able to supply a decent amount of current. Because of that, it no longer really matters how much current the input can provide and how much the next circuit eats up. Cool, but why the 1K resistor at the output here then? And what's all this additional stuff at the input? Well, unfortunately, there's other worst case scenarios we need to consider. The first one of which being a classic user error. Imagine that user plugs our envelope's output into some other module's output by accident. If that other module also uses a voltage buffer there, we'll basically create a short circuit, since buffers can not only source, but also sink plenty of current. So by placing a 1K resistor here, we make sure that in this scenario, the maximum amount of current that can flow is limited, saving our op-amps from a potential early grave. Okay, easy. So now let's tackle this additional op-amp over here. What kind of problem does it fix? Well, while we did make sure that our circuit gets enough current, we haven't thought about the voltage we're feeding it yet. We should though, because that voltage will determine the voltage range across which our envelope is operating. Think of it this way. If all our envelope does is take the input signal and make the rising and falling edges less steep, then the maximum height of the resulting curve is completely determined by that input signal. Why is that a problem? Because if the input signal would, for example, just swing between
Fuck, man, I'm so dead. I don't know why. I think I went to bed late. Oh, I kind of like that, yeah. Lol. Yeah, I just need to take like a nap, bruh. I'm so sleepy. Okay, I feel like I kind of understand the design of that. It's like not that crazy. The transistor amplifiers don't really make sense to me, honestly. Wait, that's the... I clicked on the wrong thing. It's like pretty simple. I don't know what I changed. Let's just open up the other one. Would you like to save your workspace? No. Okay, so how am I doing this? All right, let's look at the layout. Did I even route this thing? Is that auto router? That looks like auto router. Okay, I want to go to the video for the amplifier.
Input will get bigger. Because where before
So how did
the
he test
50%
it?
voltage divider was effectively halving the signal's amplitude, now we're only cutting it down by a relatively tiny margin. And second, the op-amp's output will have to push and pull a lot harder through this massive resistor to match the biggest swing at this point. Now, of course, when trying out different...
So you divide it down by 100. Or 1,000. You divide it down by 1,000 and you amplify it by 500.
resistor sizes here, it's crucial that these two pairs are of the exact same value. So they need
Oh,
to
actually,
also
no, wait, hold on.
be matched. This is the only way we can ensure that we get a 0 volts output if the two signals are at the same voltage level. In my experiments, a combination of 10K and 470K resistors worked out fine. So let's do this final adjustment and then finally take a listen. So I'll simply exchange these 100Ks for 10Ks and these other 100Ks for 470Ks. And as expected, we can now vary the output from 0 to around about 10 volts peak to peak. Perfect. Let's hear how this sounds. Of course,
Maybe I should do this from scratch because I didn't stream doing this. All right, yeah. So I'm going to open up VS Code, and I'm actually going to delete, or I'm going to move. Okay, hold on. Okay. So now, and close this. Discard changes. KiCad. All right. I can't be like. All right, let's just delete this. There's nothing in there. Okay. I can't be like accomplish nothing. Okay. All right. Here we go. Okay, so what is the first thing that I do? I forget. I'm like so out of it. Okay, so the first thing is wow, this is taking way longer than it usually does. Dude, why does it even take so long? All right, so we're going to add this, and it's, yeah, sure, we'll call it a pin. And then we'll say it's got, or fine, we'll call it a socket. Who cares? Pin socket, 1x3 vertical. There's no difference, so that's fine. Okay, so we're going to place this over here. Then type P. We're going to do ground. Okay, then P again, plus 12 volts. Then P again, minus 12 volts. Okay, now we need our op amp, which 1, 2. We only need a TL072. We only need 2 of them, but I only have TL074, so 074. Bro, I'm so bad at this. Don't want to speed run this shit. Dip 14, that's good. Okay, so we need 2 of these, then the rest of these. So pin. I wonder if we should ground. Okay, yeah, so we're gonna, okay, so what we're gonna do is we're gonna, all right, so, then what we're gonna do is, Cool. So that's set up. Now we need a CV. So let's add. Let's see. We need 1, 2, 3 of these things. So 1XO2. These are holes. So I'll just leave them as socket, and then we're gonna go down here. Solder wire. That's interesting. I need a pin socket vertical for both of them. Okay, so this is CV signal output. Okay, so the first op amp. Okay, then we want a potentiometer. And is that mounted on the thing is the question. I'm not sure.
Somewhere between 0. Now, because the resistance is fixed, we don't have to worry about it too much.
I just want to see the
unlimited additional gain. Because at some point, the potential amount of current will drop, distort, and the second option off. Up until now, curve, we were moving back and forth across this tiny section. Now what we could do is move this operating region way further up or down the curve to where it is somewhat steeper or flatter. Since this will have a direct effect on our collector current swing, we should also see a change in gain, despite the negative feedback. We'll just overpower it, basically. Cool, but while we could go through the trouble of adding our scaled-down input signal to our variable DC bias before applying the sum to the transistor's base, there is a simpler, more elegant solution. Instead of adding the bias at the base, we can just subtract it from the voltage below the emitter resistor. Because remember, for the transistor's operation, only the voltage difference between base should push up potentiometer op amp.
My guess is
now,
that
by turning the potentiometer, we can adjust the voltage at this point to any value between 0 and -2 volts. Going any more negative will probably increase the collector current too much and would thereby starve our transistor. That's why I've chosen this range. And since my oscillator is pushing out a 10 volts peak-to-peak signal, we'll also need to scale the input down with a 100K 100 ohms voltage divider. To try this out, I'll set up fire. To +12 chip, I'll slot in a BC548, which is a generic NPN transistor. The collector needs to be tied to the positive rail through a 100K resistor, while the emitter links to the op-amp's output through a 10K. Finally, I'll connect this input socket to the transistor's base through a 100K 100 ohms voltage divider. To see what's going on, I'll connect my oscilloscope to the transistor's collector, because remember, this is the amplifier's output. So right now, I've set the CV to 0 volts. Let's see what happens as I increase it. Well, this is not really what we were hoping for. There are two major problems. First, the output signal's DC offset seems to be tied to the CV and is moving around wildly. And second, the gain added by increasing the CV is so minimal, it's actually impossible to see at this scale. Bummer. So what's going on here? Well, two things. First, let's talk curve. Fire is operating. The gain is dying. For that, we could of course turn on the AC coupling on our oscilloscope. If you don't know what that is, I've put another link to an in-depth explanation in the description. But in essence, this will remove any DC offset. Let's hear how this sounds. Let's swap out the potentiometer for a jack socket. Now I can connect our VCA to anything that sends out a voltage, like an envelope generator.
yeah, I feel like we could just get rid of the bro, just how do you do it? Yeah. Don't want any fucking promoters, bro. Okay, so I think so let's see the final. All right, so let me read it. There was no CV here. So you just jumped to CV. Alright, let me read this then. To fix this, we can simply use a bit of a subtractor up amp gain. Also, we'll keep the manual CV control in the circuit so we can dial in the CV offset that gives us the sum together. Okay, I'm fine with that. I don't care. So that means that we then need... that's not what I wanted to do. There we go. Okay, so that means that we need a 1XO3 as well. And this goes to a potentiometer. Did I get the footprint on that? Of course not. Okay, now we want the BC548. We could do that, but which one did I use the other time? That one. That one's nice. I like that. All right, I'm done. I think I'm gonna like go for a run or something. This is like whatever.